stream? Okay, great. All set? Okay, great. Okay, welcome back, everyone. Thanks to the generosity of the Russell Sage Foundation, the Alfred P. Sloan Foundation, and Duke University. It's my pleasure to welcome you back to SICSS, the Summer Institute in Computational Social Science. Hello to everybody following along on the live stream. I just want to reiterate for those of you who maybe are tuning in to this topic today on automated text analysis about how things work here and how you can access the course materials. So if you're on our website here, you can Google Summer Institute in Computational Social Science. It should be the first link that comes up. And if you click on Schedule and Materials here, you'll see we're now on Wednesday. And we're going to begin here with the slides for History of Quantitative Text Analysis. And we'll be following along both with slides and also annotated code that includes code chunks or worked examples with notes that explain how to perform all the things I'll be doing up on the live stream. And again, the point of that is to relieve you from taking notes. Okay, so let's begin with a history of quantitative text analysis. And before we do that, though, let me show you what we've got on the agenda for today. We are going to, after we talk about the history of quantitative text analysis, we're going to go over a bunch of stuff that most people don't know they need to know in order to do text analysis. These are things like character encoding, tokenization, stemming. If these words are new to you, this first part of the lecture is going to be essential for you to learn how to, essentially to learn how to transform words into numbers. Okay? Then we're going to talk about dictionary-based methods. These are methods where we have kind of a known subject we want to measure in a text, and we think we can measure them by counting certain words. Then we have our break. Then we'll go over both topic models, latent Dirichlet allocation, and a somewhat new variant of topic modeling called structural topic modeling. And we'll have another very short break. And then before lunch, we're going to go over text networks, which is a new technique, a new alternative to topic modeling for automated text analysis that's going to combine some new, more cutting-edge tools like part-of-speech tagging and sentiment analysis alongside some more conventional network-based approaches. Okay, finally, we're going to have a group exercise today where we all work on the same corpus of tweets and try to come back together either here at Duke or at your local institute to discover themes in that corpus. And tonight, not here, but at Kellogg, there's a live stream lecture by Ned Smith. He's a very interesting faculty member at Kellogg, the School of Management, who is doing really interesting work at the intersection of social psychology and social network analysis. Okay. So one of the things that really amazes me about quantitative text analysis is just how much was being done in the 1930s. We all like to talk about the latest and greatest neural net or Word2Vec or what have you. But if you do some digging, as I was inclined to do before I made this lecture last year, you discover that people like Harold Laswell, the political scientist, largely after the First World War, was writing stuff like this. We may classify references into categories according to the understanding which prevails among those who are accustomed to the symbols. References used in interviews may be quantified by counting the number of references which fall into each category during a selected period of time or per 1,000 words uttered. So in other words, this is, to my knowledge, the first attempt to quantify text analysis. Now what he's describing is somewhat primitive, right? Counting which words are uttered when. But on the other hand, many folks don't know that Laswell also had people hooked up to heart rate monitor machines. and was measuring physiometric properties of people as they spoke, and measuring things like emotional activation around words. His interest, of course, in this initial post-war period was around propaganda. Later, as we'll see in the aftermath of the Second World War, security concerns also drove text analysis. So, ahead of his time, in 1935, and at the age of 21, Laswell was developing methods that track the association between words uttered and physiological reactions. Just a reminder that there are many who came before us. Or another great example is, as I mentioned earlier, the neural network, which now everything needs a neural net, right? Well, neural nets have been around since 1950. What's changed? Computing power, right? And so, of course, that has implications for how we work with text. But it's good to remember some of the genealogy of the ideas. And so let's take a moment to look at the timeline here. This is probably an imperfect effort. As you'll see, the timeline here spans many different fields, including political science, sociology, computational linguistics, computer science, information science, psychology, now machine learning, whatever that is, right? We can go back, actually some of the early pioneers, so Laswell is a political scientist, Gatsky is actually a literary theorist. Gottschalk, the psychologist, uses content analysis to track Freudian themes in texts. And of course, a big game changer was Turing in the 1950s. Some of the initial applications, actually some of the initial early development of AI, artificial intelligence, was in the realm of text, and especially text translation. Again, just by way of backstory, a lot of this had to do with the urgent need to translate foreign texts into other languages in the context of World War II and the aftermath of World War II. And so a lot of these early efforts were trying to train some of the first natural language models. Didn't really become institutionalized till 1952. We started to have textbooks about content analysis. People were slowly and gradually beginning to be trained in content analysis. 1954, we have the first successful automated translation of a text. 1963, again, some early political science pioneers use quantitative techniques to analyze the Federalist Papers. And again, more formalization of narrative analysis in quantitative format by literary theorists such as Tomaszewski here. And then we go into the 1960s and 70s, and what changes? Well, again, neural nets have been around. A lot of the principles of AI have been around, but computing power is changing rapidly, right? So Stone and Bales used the first, no relation, used the first mainframe computer to measure psychometric properties of text at RAND, right? And then there's a really big moment. So the famous linguist Noam Chomsky at this time is really producing what is viewed by many as a single theory of human language, right, that could be used to explain and interpret any utterance given universal laws of language, right? And at the same time, people are kind of figuring out that that might not be possible, that might have been a little bit of a reach, a general theory that could always infer the meaning of a text given its relationship or its adjacency, say, to other words, right? People continuously realize that in natural language use, words take on different meaning based upon their co-appearance alongside other words, and that words are highly context-based, and that there is polysemy, that is that words can mean different things to different people at different points in time, right? And here's where the field of natural language processing is born, alongside advances in computer science. The field of computational linguistics is born. The first part of speech taggers come on at large scale. And these types of things become used by political scientists and others doing automated event coding. Another big development is The linguistic inquiry word count software is created in the 1980s as an attempt to measure sort of universal psychometric properties of text. And finally, some exciting things start to happen in network analysis by Roberto Franzosi and others. And really, it wasn't until the 1990s that we started to talk about topic modeling. One of the classic papers written in the Journal of Machine Learning by David Blay. But around the same time, sociologists such as Peter Bierman, Jim Moody, John Moore are also developing network-based approaches for text analysis. 2003, we get more infrastructure like Mallet, which is a system, one of the early systems for running topic models on text. And then slowly and gradually, somewhere around 2010, when I was really beginning my career, you saw these methods just vault into the mainstream. Topic modeling, sentiment analysis, really started to show up in a lot of journals. In some disciplines earlier than others in social science, but really came to be viewed as a really major and important tool in the social scientists toolkit. And there was, at the same time, a bit of a hype cycle, right? So yesterday we talked about some of the strengths and weaknesses of digital trace data. And we talked a lot about how many people were arguing at one point that the size and the scale and the various strengths of big data meant that we won't need theory anymore, right? And we talked about why we don't think that's wrong. We think we might need more theory, right? Well, the same kind of thing is happening in text analysis. People are saying, well, now we don't need to read anything anymore, and now we don't need to. In the extreme version of this, now we don't need to do interviews anymore, and we don't need qualitative researchers, right? And now, those of us who have been involved in kind of bringing or trying to import these methods into mainstream social science have very quickly realized that these methods will not do that. The analogy I love is from David Blay. If you talk to him about topic modeling, he'll say it's a tool for reading, right? Machines are not yet at the point where they are going to do the interpretation for us. With some assumptions and with some patience, we can do great things, and we will do great things today. But we need to put some cold water on some of the hype cycle, and again try to reach the plateau of productivity that Matt and I have been talking about for the whole week. Okay. So it's an inherently interdisciplinary field. I'm sure I left some people out. If those of you watching or here have some additional events left out, please Slack them and we'll add them for the website. Okay, so let's move along. We're going to talk now about basic text analysis. So I'm here on the slides, but if you want to follow along with the annotated code, that link is also available immediately to the right of the slides link. Okay. So yesterday I mentioned that many people spend a really long time cleaning data instead of analyzing data, right? I mentioned in particular a survey of data scientists by the New York Times some years ago that suggested that data scientists are spending on average somewhere around 80% of their time cleaning data and 20% or less analyzing it, right? And so this is definitely true in the world of text. Text, as we saw yesterday, when we did some screen scraping or some of the other methods we talked about, we produced some pretty messy data, right? It had unfamiliar structures. It had messy, indecipherable language like HTML tags. And so one of the first things we need to do, which actually turns out to be a somewhat involved process, is to figure out what's going to count as the unit of analysis and how are we going to go from unstructured text to ones and zeros, which is what we're ultimately going to need to run models on text. The joys of character encoding, let me tell you. So just like yesterday, we talked about how a web browser, what a web page looks like to us versus what a web page looks like to a computer. And we noted in particular that the HTML code has all these instructions that we are not seeing, right? That hidden deep in the guts of the HTML is usually the information that we want to extract, right? So similarly, when we are talking about text, text actually has different digital identities. So for example, this chart here displays a few different examples, actually more than a few different examples, of character encoding. And character encoding is essentially a data format that allows something like a web browser or a word processor, or say a spreadsheet, to visualize a text. That may seem commonplace, and you may be asking, or it may seem arbitrary, right? Or why don't we have one system for all text? That would be great, right? The problem is that texts are produced in different languages, on different computers, at different points in time, on different operating systems. And so all this means that we have this awful, messy soup of character encodings. And when we're working with text, a very common problem is that we have text in multiple character encodings, or that we're simply unaware of the issue of character encoding. And we get strange, indecipherable error messages such as invalid multi-byte string. We hear about UTF-8 or Latin 1 or ASCII or all these kind of strange error messages, right? These are a genre of error messages which are telling you that the format that your text is in is making it difficult for your computer program, be it in R, Python, or wherever, is having trouble reading in your text. So there's no great solution to this problem that I know of. It can be difficult to detect character encodings in text. There are various packages that I've seen, and if others know of alternatives, please Slack them. In R, for example, there's an encode, E-N-C-O-D-E function, but it works, I don't know, in my experience, 50, 60% of the time. And that's because it's trying to make a guess of the character encoding based upon the actual bytes that are in the data that we're looking at. So we'd love to do this programmatically. We'd love to take our text and just instantly put it all in the same character encoding, and we can do that. We can do that with things like, if you're in R, the iconv utility in base R, iconv, and this will allow you to take a string and then specify the format, the character encoding you want to move to. The problem with this technique is that when we coerce one text into a different character encoding, if, for example, we have a foreign, let's say a non-English letter, right, which has some type of accent on it, like an umlaut or an accent aigu or something like that, right? We then may accidentally create a string of numbers or punctuation marks or other text markers that are telling you, essentially, that the character encoding you've chosen can't visualize that character. And so sometimes when we coerce all our text into a single character encoding, we wind up with even more mess, okay? So you'll see as you work through some of the examples today, there's some, I like to put in real-world messy examples in our code, because my experience is I could get everybody topic modeling pretty quickly with a nice, neat, curated data set, but then when everybody goes to do it on their data set, they get a bunch of error messages. They don't know how to generate the data set that they need, and that turns out to be, for many people, especially many beginners, a real stumbling block. So you'll see in one of the examples we work through later, it is a set of blog posts that have been scraped off of a number of different blogs. And each of the blogs uses a different character encoding. And so what we see at the end of the day is a really messy set of text that has all sorts of strange characters in it, right? That's yet another reason maybe to avoid screen scraping these days, right? Remember, with screen scraping multiple sites, we have to navigate the different structures of each site and then write different parsers to extract the part of the source code that we want to include in, say, a text analysis, right? And so if we work with APIs, typically speaking, we get a much more consistent character encoding. So Twitter, for example, should deliver all of its text in the same character encoding. And you may have noticed yesterday in our example, when we pulled data about Korea, we were able to see Korean when we browsed the data, right? And that's because Twitter has chosen a default character encoding, I think, in its API that has allowed it the flexibility to capture not only a range of different languages, and remember there are many, many languages in the world, at least 72 that are used by very, very large groups of people, right? But also language is changing, right? So things like emoji. It turns out we need new forms of encoding to capture those emoji. And if you're doing a study where a certain emoji may carry a lot of meaning, I'm trying to imagine such a study, but I could take a few guesses, right? Especially, let's say we were studying abusive behavior online among teenagers, right? That might be a really important thing to capture. And so you would need to work with a character encoding that can capture those emoji, because ultimately what we want to do is recognize discrete words as individual units of analysis. And if our emoji gets deleted or otherwise transformed in some kind of analysis, like coercing one character encoding into this, coercing all text into the same character encoding, we could do some real damage to our analysis. So anyways, character encoding, it's just a ton of fun. And much like screen scraping, it's one of the more frustrating parts of working with text. But again, many of these issues have been solved with APIs. It's just something to kind of file in the back of your mind as you begin to work with different texts. You may be experiencing character encoding issues. OK, so in addition to character encoding issues, you may just have messy text, right? Like yesterday, you may recall when we scraped the Duke webpage, we had these kind of funny /t/n at one junction. And I explained then that those are these things called HTML tags, which are telling the browser to, for example, start a new line before you put text, or put a few spaces before you put text, right? And so one thing we might want to do once we get that data is to begin to clean it up. And so and kind of indispensable tool in your toolkit when you're doing automated text analysis is grep, or more broadly regex, or regular expressions that allow you to perform various transformations of text, search for patterns in text, and more generally to clean text in various ways. So here's an example of what I was just talking about. This was actually not a Wikipedia script. This was from the Duke page, but these are the HTML tags I was talking about. And so let's just work through a really simple example. Let's say we want to clean up this data. There are, by the way, packages that will do this for you and remove all HTML tags. So there's probably better ways to do this. We're just working through things incrementally to develop your skill set. Well, we can do things like first search for a word. So here, this grep-l command is searching for the word class in our object, which we've mistakenly labeled as Wikipedia scrape. And it returns a Boolean value, right, that we can see that class is in the string Wikipedia scrape, right? And that becomes useful because we can, for example, look for patterns in text. And we could, for example, subset a data frame using this command grep-l, or we could otherwise restructure or reshape data. And we're going to do that when we get into dictionary-based approaches in just a little bit. But let's return to the example of cleaning up this HTML data. Let's say, for example, we want to get rid of these /t's here and replace them with nothing, essentially delete them. Well, there's a grep-style command called gsub in base R that would allow you to input the first argument is the thing you want to replace, and the second argument is how you want to replace it. and the third argument is the character vector, in this case, this string. And as you can see, when we apply this gsub command to that text, we've eliminated the /t's, right? And we can also use a variety of operators in our regex here. This vertical pipe indicates or. So here we're saying remove either /t or /n. And there's going to be a ton of different symbols that one can use like this to search for patterns in text. We don't really have time to go through all of them. So for example, you may want to find out words that begin with P in a text, right? This caret here is the way that we would indicate in a regular expression form that we are looking for. We're looking in this text that we've called some text to see whether or not there are any words that begin with capital P, right? And we could do the same with numbers. We could do the same with lowercase words, uppercase words. And this might all sound kind of obscure and unnecessary, but as you'll soon see, sometimes removing numbers from text is really critical if we don't think they're going to add value to our text analysis. And so again, we don't have time to go through all of them. So instead, I'm just going to point you to a really helpful cheat sheet linked here. This is a regex cheat sheet that will show you dozens and dozens of different ways of transforming text. Again, we're going to learn about tools today that do a lot of the important cleaning for you. But it's almost always the case that at some point when people are starting out in text analysis, that they just don't know about grep and regular expressions. They don't know about character encoding. It's just a classic stumbling block. So check this out when you get a chance, or maybe file it in the back of your mind that when you're looking for patterns in text or trying to transform text, it's going to be really useful to check out regex, regular expressions. One other quick thing that's a bit frustrating, can be a bit of a nuisance, is when we use these regex, right, we may actually want to transform a character, like let's say this backslash, that has a meaning in a text, right, to the computer, as a regular expression. So if we want to do that, we would need to use some pattern of, and I think I've got an error in this slide here. I was trying to say, let's say we want to remove these brackets here. We need to use some type of pattern to tell, in this case R, that we want to treat this backslash as a character and not as an instruction about something to search for. And so to do that, there's a variety of options. It gets complicated because the conventions come out of different coding languages. So for example, there's a Perl approach that is slightly different than the one used by R. And so it will be useful, again, to read a little bit about how to escape text. If you keep trying to replace, say, a bracket or a punctuation mark and you can't, you're likely dealing with a character escaping issue. Right. And here's an example of how you might escape the bracket here in R. And for those of you who are new to R, you can specify a Perl equals true argument that will give you the Perl regex if that's what you prefer. Okay. So that kind of takes us through some very basic concepts in cleaning text and getting used to these new concepts. We still have a lot more to do, though, before we can get to running models. And that all has to do with figuring out how we want to think about what counts as a unit of analysis. So this is broadly often referred to as tokenization, right? If we have a sentence, like this sentence, linguists are kind of uncreative in how they come up with examples. Sorry, I probably should come up with something better. But you know, we can think of the unit of analysis as a sentence. We can think of it as a word. We can think of it as a sequence of words, or something we might call an n-gram. And so we make decisions when we analyze text about what's going to count as the unit of analysis. Very often, or even most often, we're looking at tokenizing by words. But even after we do that, or sorry, n-grams, which again are sequence of words. So this sentence can be tokenized in 3 different ways, right? It could be, if we're just using unigrams, then each word is a token. If we're using bigrams, then this is a token, is a token, and a sentence is a token. Why might we want to use sequences of words instead of individual words? Well, there are some times when sequences of words can really change the meaning of a sentence. So for example, if I were to say, I'd hate to be the president, that would have one meaning. And if I say, I hate the president, right, that would have a very different meaning, right? And that to be turns out to be critical in changing the meaning of that sentence. Now, we could debate about whether, when we take this to scale and look at large groups of texts, right, then are we really, going to be worried about that? Well, how many times is there that kind of complex sentence construction that might transform the meaning of a sentence? It's something that's probably unknowable if you're looking at a really large corpus. The convention is to kind of pretend that's not a problem. There's some newer research going on that says it might be a problem. As you'll see, a lot of the decisions we're forced to make are somewhat arbitrary, and we need folks like you and you all watching on the live stream to do the studies to try to look at some of the sensitiveness of these decisions. Okay, so once we've tokenized and we've decided what's going to be the unit of analysis, we need to create some type of new object, some type of new data structure that we can run a model on. One of the most common data structures is a corpus. A corpus is a data object that includes both individual documents and then the entire set of documents. And very often we need both. We need to make a comparison between an individual document and then an entire group of documents in order to make guesses about what types of themes exist in those documents. And that's why we need a kind of somewhat unique data structure. And so corpuses can be made in a lot of ways. I forgot to wrap the text here, but we can load, if you want, from my GitHub site, a database of Trump tweets that were collected about a month ago using the methods we discussed yesterday. And we can look at just a few of them here using our head function, try to get a sense of the data. And the data is in a data frame format. And so if we wanted to create a corpus of these tweets, we could use something like the TM package or text mining package in R. Uh-oh, shoot. My slides are broken. Darn it. Sorry, everybody. Let's see here. I'm going to switch over to the annotated code. Well, some of the TAs hopefully help me get that back up. And we'll kind of walk through the code instead of the slides here. OK. I just remember tokenization, creating a corpus. OK. So here we are. We've installed the TM package. And we need to load the package, of course. And then to create a corpus, which is, again, a data structure that we need to do things like topic modeling or even some more basic forms of text analysis, like dictionary-based analysis, we can use this corpus function within the text mining package. And here you'll see that each corpus also can store metadata, things like the name of the author of a text or the time in which it was written. And those might be useful because very often what we want to do when we do a text analysis is, say, plot changes in themes over time, or to look at differences across authors, or this type of thing. And so having this type of metadata in a corpus can be useful, especially when we get into structural topic modeling, which is a form of topic modeling that exploits metadata in order to improve classification of unstructured themes in text. OK, there's a new nice alternative which has come online in the last year or two. And this is a new data format called TidyText. So we've been working a lot with techniques from the tidyverse family of methods. We've worked with ggplot. We've worked with dplyr. We've worked with rvest yesterday for screen scraping. And TidyText is a really nice package that basically provides an alternative to the Corpus object, which tends to be clunky and can be difficult to work with, and it can be difficult to import and export data and run some more kind of basic analyses. And so TidyText is a simple concept. The idea is that we store text as a single data frame, and each line is a word, and then we store metadata, which describes which document the word comes from and which order the word appears in. And so instead of having many documents and metadata, we have all of the data in one long data frame. And you'll, of course, need to install TidyText if you want to follow along here and load TidyText. We're also going to use dplyr in this example, which is a tool for data reshaping and restructuring. And here's one of the core functions in TidyText. Now, for some of you, especially if you haven't used dplyr very often, these instructions here might be a little unfamiliar to you. These are called pipes. And what we're doing in this sequence of code is passing output from one line of code to the next line of code. And so we are taking the Trump tweets data frame that we read in from GitHub, and then we are subsetting it by date. And then we are taking that same object and applying a function called unnest tokens from the TidyText package. And what that does is transform a text into this TidyText format. And we're assigning all of those instructions to a single new object called tidy Trump tweets. You gotta love the alliteration. Okay, so what does that look like? If we browse it, we'll see the date, the word, and again, something about the word order, or sometimes just the word order appears consecutively. So if we want to do some very basic analyses, one advantage of TidyText format is we can make very simple data frame calls to do that. So for example, this code is simply counting the most popular words in our TidyText object here. And somewhat unsurprisingly, the top words are the, to, and, of, and HTTPS. And again, we're using some dplyr here to both subset our text and then to sort it by the most common terms, right? And so again, if you need some background on dplyr, the data camp is great. If you're coming from base R and this is moving a little fast, these pipes take a little bit of getting used to. Okay, so as you can see, if we ran a text analysis on these data, we would run them to a number of problems, right? Most of the units of analysis would be words like the, to, and, of, even worse, HTTPS, right, which is just presumably like Trump linking to, President Trump linking to something. TCO, which is a sort of Twitter-specific way of linking to stuff, right? We wouldn't really, any type of model we tried to build to classify this text would say, well, every document has the in it, or every document has a in it, right? Or even most of them do. So what does a mean? I can't figure it out, right? We have to think like a classifier here, right? That's gonna create a lot of trouble for us. But more importantly, you know, if everybody's using the or everybody's using and, it's unlikely to really help us tease out meaning in a text. And so one of the very first things that's often done when we're moving to an analysis is something called text preprocessing. So we will, you know, very often make decisions once we've got our data in, say, Corpus format or in TidyText format. We then make a bunch of decisions about what we want to count as words. And so these words, the, and, bot, for, and so on, are often referred to as stop words, meaning words that can be dropped or avoided in an analysis. And These will be language specific, of course. So we'd have a different set of stop words in French or German. And in some languages, such as Chinese or Arabic, these stop words become even more complicated because of conventions around punctuation and verb tense and so on and so forth. If we're looking at the world's major languages, English, French, or maybe not French, English, Chinese, I guess not so much many of the South Asian languages, but most of the European languages, Spanish, French, German, Italian, these are all pretty well supported in the natural language processing world, meaning that people have built tools, language-specific tools for working with these texts. Arabic as well, Russian as well. Okay, so we're going to be working through an example that uses English stop words, but with a little bit of elbow grease, you could discover lists of words that are typically avoided in other languages as well. Usefully, the TidyText package and the Corpus package have built-in functions to remove so-called stop words. So if we're in the TM package, which is what we use to create the Corpus object, there is a function called tmmap. And when we apply it to a Corpus object, in an earlier step, we define that object as trump_corpus. And then we can apply a function to that. This function is called remove words. It's simply going to drop a list of words from the documents in the corpus. And here in this package, we can call a list of English stop words as follows. And I believe we can also call lists of stop words in other languages there. I tend to use TidyText, so I don't have it on the tip of my tongue. But I believe we can specify other languages here. And to look at which languages are currently supported, I would encourage you to browse the documentation of the TM package, which is pretty well supported online. There's a lot of vignettes and worked examples and so on and so forth. And similarly, there's a wonderful online free resource for TidyText that was recently put out, which is wonderful as well. And in the TidyText package, there is a data frame called stop words, which is attached with the package, meaning when we load the package, we can load that data set. And so that's what we're doing here. And we're using the dplyr anti-join, which takes one object here, the tidy trump tweets object that we made in a previous step. These are the trump tweets where each row in the data frame is a line, and removing any line that contains one of the stop words. Yeah. And now, after removing the stop words, we can take a look at our top words once again, using some dplyr, the same dplyr again up here, right? And we still have some stuff we probably don't want, right? HTTPS and t.co and AMP and RT for retweet, right? But now this is starting to look more recognizable, right? People, news, president, fake, Trump, country, and so on. Okay, so we're getting there. If we wanted to remove terms like HTTPS and t.co, we could do that in a number of ways. We could add them as a word in the list of stop words, or we could remove them using grep-style commands. Okay, another decision we need to make, though, in addition to stop words, is thinking about punctuation marks. And here's the best joke ever. Let's eat, Grandpa, and let's eat, Grandpa, right? These two phrases have very different meanings, right? Okay, it's not that great a joke. It's hard to make jokes about natural language processing. Okay, so and what's giving it the different meaning, right? This critical comma here. And so usually in the world of natural language processing, we just pretend these punctuation marks don't exist. We just drop all of them. We eat Grandpa. And so again, I think we need more research on whether this step is reasonable. It's just become common practice. And I don't know, again, if people know, please share in the Slack any resources on removal of punctuation marks, but as far as how they change the meaning of an analysis. Here's how we would remove punctuation marks in the Corpus package, using, again, the TM map function and a function called content transformer. And the nice thing about TidyText is that it will automatically remove punctuation marks, though we can specify how not to do that in the unnest tokens function if we want to. OK, numbers. Very often we might also want to remove numbers. And the way we would do that in the Corpus world, or the TM world, is as follows. Here we're just applying a function called content transformer and a function called remove numbers that's just going to drop all numbers from our text. Here's how we might do it in TidyText using some regex that say anything that has a space and then numeric digits and then another space, we want to drop that. Again, we could talk about whether removing words has an impact, right? Removing numbers has an impact, right? If we remove 1776 from a corpus about American political discourse, that might have significant consequences. And if we don't, then it may be fine. Again, this is widespread convention, and there's not great work on the consequences that I know of. OK, next, word case, right? Do we want to treat a word that's uppercase the same as a word that's lowercase, or that starts with an uppercase letter? Once again, typically, we don't care. That's the convention. But there's examples like the word God, right? If someone capitalizes the word God, it may indicate that they're a more religious person. If they make God lowercase, we can think of examples, right? And the question we need to think about is, at scale, when we look at large groups of text, how often is this going to distort our analysis? We can move all text to lowercase in the TM package as follows. Once again, TidyText does that automatically for us. Finally, next, with all this messy data and all these transformations we're doing on data, we very often wind up with a blank space as one of our words, units of analysis. And I can't think of a case where we would really want to care about a space, but maybe there's one. And so we also very often in a stage of text preprocessing will strip all white space from a word. We can do that in the TM package as follows, and in TidyText as follows. Finally, I think that's the last thing. Yeah, phew. OK, finally, we talk about stemming. We are going to want to make decisions about whether to take different tenses of words, especially, as having a different meaning as other tenses. So let's think of the word run and the word running, right? We could wonder whether both words are about jogging, right? And we might want to say that really, if someone talks about, let's go for a run, and I just went running, and we're in this very strange example trying to measure, discourse about exercise, we might just want to treat those things as the same thing, right? We might also wonder whether someone's running for president, and that's a whole other genre of issues. But let's say we've decided that we want to treat running and run the same. Very often we do that through a process known as stemming. And in the very simple version of this technique, we simply drop things like ing from the end of a word. That's the common approach is known as a Porter stemmer. But there are more sophisticated forms of reducing words to their conjugate form, such as lemmatization, which is essentially just a more it takes into account the network structure, a semantic structure of words in a more sophisticated manner. We'll use those in some of the techniques we talk about at the very end of the lecture today. But in principle, it's very similar to stemming. We don't want to think about word tense when we're doing these analysis. Or maybe we do. Who knows, right? I don't know. And I'm supposed to know, right? That's bad. OK. Here's how we would do it in TidyText, and the example above in the Markdown tells you how to do it in the Corpus package. We're going to run a little bit over time here. I apologize because of the technical snafu that we've had. But we have to get through a few more things before we can get into the fun stuff. The first is, OK, so we've gone through all this mess. We've gone through character encoding. We've gone through things like HTML tags. We've made decisions about tokenization, about stemming, about punctuation, about word case, about white spaces. We've made all these decisions. And now we need to actually go from words to numbers. We need to have some type of typically matrix representation of our text in order to run a model like a topic model, or even a text network, or even in many cases a dictionary-based analysis, though not always. And so the way we do that typically is by creating, at least in the case of topic modeling, is to create something called a document term matrix. And a document term matrix in the text mining package, TM package, is created as follows. Here we're taking the corpus object, and we're saying which words we want to include here. We want to include every word that's more than 2 digits long. And if we run this line, we can inspect the output, and we'd see an object that has on the columns a list of every word that appears in any document, okay? And in the rows, the names of all the documents. And then the cells of that matrix are going to be a count of the number of times that that word appears in that document. And so you can think of this as a single giant matrix that describes all of your documents in one efficient form. And we're again going to use that to learn and detect themes in text. OK, and to create the document term matrix in TidyText, here is the code you would use. And I should note much of the annotated code have examples for you to practice with later that are called Now You Try It. Don't try them now. This would take a bit of time. But maybe, again, if you're working through this later, or if you're following along with us on the live stream, you could pause and then come back and try this out. OK, so we are just, I think, how many minutes over are we? Oh, we're not. Oh, we're supposed to end at 10:15. Oh, OK, great. So let me pause and ask if there's questions. Yeah. Mm-hmm. Yeah. The or? So the question is, in the very beginning when I was talking about replacing characters, if you needed to replace the or character, you mean the vertical pipe? Yeah. Yeah. So this is a case where you would want to escape the text. So you need to use either one common way is 2 forward slashes before the digit you want to replace, and then 1 single slash, or single quotes can be used. But you'd have to find the regex to escape that vertical pipe. There can be, this again is a frustrating thing to do. It usually just takes a little, referencing one of these cheat sheets, or Googling it to, how to escape a vertical bar in R, something like that, when you get lazy, yeah, like me. We are over time. OK, great. OK, so any other questions? So we're doing that? Oh, yeah. I'll just take a few more questions, and then we'll
various languages. Oh,
yes, OK.
Yes. So is there a standard encoding for that? Because I had experience in my previous project. We had data from more than 40 languages. And I just used UTF-8, and it worked most of the time. And usually when I work, for example, with data in Russian, for example, I work with UTF. So usually it works. But maybe there can be cases then it won't work. So is there a standard approach?
I think UTF-8 is a great choice. So the most languages I've ever worked with is 72 languages. I have a study that examined Google search terms in 72 different languages, and we use UTF-8. The only limitation I can think of with UTF-8 is it may be limited with regard to more colloquial or current word usage like emoji. But maybe others have more up-to-date knowledge on that.
Then question about emoji.
Yeah.
What is the encoding which covers that?
Oh, I don't know the name of it
don't
off the
know?
top of my
Okay,
head. Yeah,
okay.
I would just search for character
Okay.
encoding, emoji, Twitter, because the problem is different social media sites
Yeah,
have
yeah,
different emoji, right? So then they each have different character encoding, which is a
Okay.
true,
Thank you.
true nightmare, yeah. Any other questions? Yeah, Natalie.
I was wondering about term order.
Yeah.
So the matrix you talked about is presence or absence of a given word in a
Yeah.
given document.
Well, it's a count of the words. So it's not just a 1 or a 0. It
Right.
could be like a 12 or whatever. Yeah.
But it's not about, like in tweets, you could be interested in whether they use the word I before the word people or something like that. Do any of these functions that you're talking about get at the order of 2 particular words you're interested or 4 particular,
Yeah. So if we wanted to tokenize by n-grams, for example, we could get it word order. And there's some attempts to do that. In the topic modeling world, there's some papers that tokenize with n-grams and typically find not wildly different results, but the problem is usually it's often the case that you want some of the n-grams, but not all of them, right? So you might want we the people, right? That might have a signal as something American, right? But then you don't want and the brown fox, whatever, all that other junk, right? And so there, you'd really probably need to get into the world of part of speech tagging, which we'll talk about briefly towards the end of today, in order to extract something like, most often you'd probably be interested in like noun phrases or compound nouns. We the people, the United States of America. Sorry, all my examples are American today. You'd probably be best served with a package like Phrase Machine, or we'll introduce you a little later to the TextNets package, which has capacity to do part of speech tagging. But probably you'd then need to make difficult decisions about whether you want to tokenize according to those phrases or individual words. And certainly you can tokenize by phrases. And that's something some of the papers we'll discuss right before lunch. We'll do that. Yeah, it's a good question. Any other questions? Nothing from the live stream? Okay, I think, is it a 15-minute break planned? Can someone please check for me? So, okay, so if we could please come back at, I guess we should do 10:30. Then I guess our second break will be pushed back a little bit with apologies to everyone following along in other locations. Okay, I'll see you at 10:30.